Every single day, satellites photograph the entire surface of the Earth. The private firm Planet alone maintains a 6-petabyte archive of imagery, utilizing hundreds of small satellites to refresh the map of the global landmass roughly daily. To a human eye, those orbital shots look like incredibly detailed pictures of cities, rivers, and coastlines. But to a computer, they are not pictures at all. They are massive tensors, grids of numeric pixel intensities spread across different bands of light. You cannot ask that grid of numbers a question. You cannot write a standard database query asking for a list of flooded roads or the exact count of new buildings from a raw photograph. We have captured more data about the Earth than humanity could ever manually review, but uninterpreted pixels offer no immediate answers on their own. Historically, solving this required a human aerial surveyor. You hand them a raw photograph of some terrain, and they study it, analyze the shapes, and hand you back a structured map. This diagram illustrates exactly how that translation works. On the left, the raw grid of numbers, and on the right, a labeled map. Down in the legend is where the value lives. It assigns clear names to arbitrary shapes, water polygons, ships, and changed areas. Geospatial AI essentially acts as a surveyor that never sleeps. It operates at a planetary scale, scanning the globe and writing its legend directly as queryable data. This schematic outlines the pipeline. Stage 1 is tiling. A satellite scene is chopped into small chips with precise metadata. In Stage 2, each chip passes through a vision transformer, compressing raw pixels into an embedding, capturing physical meaning, not just color. This training is self-supervised. By hiding patches of imagery and forcing the model to predict what is missing, the AI learns physical structures without human-provided labels. Stage 3 is labeling. Segmentation paints pixels with classes like water. Object detection draws boxes around vehicles, counting them. Change detection calculates what moved. Finally, structured output. Labels are serialized into GeoJSON polygons, database rows, and automated alerts. Raw pixels enter one end of the pipeline, and structured, easily searchable facts exit the other. This graphic shows the foundation models. Prithvi EO 2.0 uses spatiotemporal embeddings to track floods. Clay, trained on 70 million chips, creates reusable location embeddings. Alpha Earth Foundations fuses optical, radar, and elevation data into a single, global 64-dimensional embedding field. Because these base models already encode Earth's geometry, training them for highly specific downstream tasks requires only a tiny fraction of the human-labeled data older methods needed. The industry standard has shifted. The raw optical image is no longer the primary asset. The pre-computed multidimensional embedding is the true reusable product. Here is the International Space Station. In 2026, researchers successfully compressed the Prithvi model and ran it directly in space aboard the Imagery payload. Moving inference onto the satellite cuts latency. Instead of beaming down terabytes of raw pixels, the satellite processes the scene itself, transmitting only a lightweight text file containing the answer. Over Alice Springs, Australia, Planet achieved a similar milestone, running object detection on board its Pelican 4 satellite to identify aircraft in real time, right at the source. This shrinks the timeline of geospatial intelligence. A process that once generated a delayed weekly report can now fire an immediate automated alert. Looking back at the top tier of our diagram, we see the final piece of the stack, the reasoning agent. Google Earth AI uses a Gemini agent sitting above the foundation and labeling layers to actively read the map's legend. A user can type a natural language question, like asking which specific neighborhoods are most vulnerable to a recent flood. The agent receives this and immediately breaks it down into a multi-step execution plan. It begins orchestration by calling out to specific specialist models as tools. It pings remote sensing models for flood extents, queries weather models for upcoming rain forecasts, and pulls demographic numbers from population databases, all simultaneously. In the fusion phase, the agent combines these separate data streams into one coherent output, returning a list of damaged buildings, a verified flood polygon, and a precise ranked list of where relief efforts should go first. It is a complete perceive, reason, plan, and act loop applied to the physical surface of the planet. There are strict physical limitations here. A model operating on imagery with 30 meters per pixel cannot count individual cars. The final data is permanently bound by the resolution of the sensor. Heavy cloud cover, sensor noise, and a lack of ground truth data still constrain accuracy. An AI model parsing bad optical data will simply produce a highly structured, highly inaccurate map. Most importantly, this entire pipeline remains a perception layer. It provides the map and categorizes the physical reality on the ground, but it does not make the executive decision of what to do about it. But once the planet's raw pixels are successfully translated into a live database of queryable facts, the inevitable next step is an autonomous agent programmed to take physical action based on that real-time map.